Hey everyone! Today we're diving into a topic where passive house designers really in their keep. I'm talking about thermal bridging.
In the simplest terms, thermal bridging is a break in the thermal continuity of your building envelope. It's where heat escapes faster than it should because it always follows the path of least resistance.
There are plenty of culprits: stud, material changes, penetrations, and especially corners.
The problem becomes more critical in high-performance building. For example, in a poorly insulated house, one bad detail might cause 16% heat loss, but in an R45 wall, that same flaw could mean up to 35% heat loss. That's why eliminating thermal bridges is one of the best investments in passive house design. You get the most benefit with the least resources. Oh, and by the way, cantilever concrete slabs? A passive house designer's worst nightmare.
So why worry about thermal bridging? Simple. It can throw all of your hard work of designing a low energy building and cause surface temperatures to drop, leading to condensation and mold. Now, there are two main types: linear thermal bridges, which are found along the length of balconies or corners, for example. We measure this with psi value. This one is also divided in two groups.
Geometric, that's when the shape changes dramatically, like a 60-degree turn. Constructional, when insulation is penetrated and standard calculation just don't cut it, and there is point thermal bridges, like a column punching through the floor. Now these are 3D and measured using chi value.
Passive house aim for a thermal bridge free design, or at least so low that is basically negligible, like below 0.01. So I've been referring to psi value a lot, but what exactly is it? Well, it's essentially the loss through an assembly, a function of U over the surface, meaning U by A.
And if you're wondering whether to use internal or external measurements, that's a trick question. There is no right answer, but PHPP use external ones to prepare for a worst case scenario.
Here are the 3 steps to hit passive house level. Inspect visually, then verify with a thermal image or a probe. Compare your detail to those in the passive house catalog. Simulate using tools like Flixo, which passive house also offers a course for.
The PHPP software applies correction factors for construction quirks, but note these do not always impact in a negative way. Just note, constructional bridging only works with 2D simulations. Your well-known formulas, sometimes they won't cut it. Let's go back to point bridges. Even screws can wreck your insulation performance. Now, for example, an insulated wall rated R39 might drop to R35 just from screws alone. Now, that's nearly 20% less. Thankfully, options like fiberglass clips can eliminate the need for screws entirely, achieving almost 100% effectiveness. Other types of attachments have different effects on your thermal performance.
If you are from a warmer climate, then this is probably new for you. Frost walls are important. They essentially prevent soil from shifting due to freezing, but they can also be the reason of significant thermal bridging.
See this? No thermal break between the frost wall and the stud wall equals big problem. Now what's the solution? Interior foundation insulation or a frost skirt like XPS around the base. Prefab options like ICFs, which means insulated concrete forms, are becoming more popular in North America and can help simplify things.
Now let's talk about roofs. In places like here, for example, with a lot of precipitation, we love pitch roofs, but they can also mean a problem. What is a great solution? Well, you can use raised hill trusses, or also called energy trusses, which basically elevate your roof so the thermal envelope remains continuous.
Or use thermal bridge-free rafter tails, strong enough to support the roofing material, but let the thermal layer run uninterrupted.
Now, here is the big enemy: balconies. Everyone loves them, unless you are designing a passive house building. They are the number one reason for thermal bridging in your building.
Maintaining insulation through balconies is tough, but doable. Prefab balcony connectors or structural thermal breaks are lifesavers, especially in high rises. It might be difficult, but balconies are a big selling point, and there is no developer who will accept not building it. So, we need to learn how to solve this.
Windows are another critical point. Good detailing and extra insulation are key to minimize bridging. You will see why this is a common trend with Windows. Almost every challenge that we have to achieve Passive House standards can be seen in Windows.
Want to see the impact? We ran 2 simulations in PHPP, one with Passive House detailing and the other one with just standards. Results? Heating demands nearly doubled, and the building failed Passive House standards.
Thermal bridging might just be Passive House's most important topic. That's when a Passive House designer actually earns their fee. But the best part? A well-detailed solution costs the same as a poor one. Thanks for watching. The next topic I'm going to cover in Passive House is actually going to be about Windows, which is also one of the most difficult topics in Passive House. See you in the next one.